In this class today, we are going to discuss about a very important spectroscopic technique called Raman spectroscopy. And as you know, Raman was an Indian, and a lot of important aspects are involved in relating this spectroscopic technique. So, I will be able to do a little bit of justice to this in 1 hour time, but I do not think it is possible to talk about the details of the spectroscopy in just a short span of time, because there are a lot of added theories are needed to be covered in such a class. But I am going to give you some basic idea of the spectroscopic technique, how it can be related to applications, and obviously some amount of instrumentations will be dealt with. As you know, the outline is like this. Obviously, there will be some aspect of introduction going back to history and some basic features, and then I will talk about some basics of the Raman spectroscopy, where I will talk about theories, and then some amount of scattering and vibrations, and finally some instrumentation for Raman spectroscopy. And obviously, during the course of the lecture, I am going to talk about some examples from the literature and from some of our own work. As far as the basics are concerned, Raman spectroscopy basically probes the vibration modes of material. It is more like an infrared spectroscopy. I have already discussed about infrared spectroscopy in a few classes back, and there I showed you by theoretical presentations that how this IR spectroscopy related to the vibration modes of the molecules. But there is a distinct difference between IR and the Raman spectroscopy. In fact, in IR spectroscopy, the bands arise from the change in the dipole moment of the molecule, but Raman's bands arise from a change of the polarizability, not the change in the dipole moment, remember. So, it is the polarizability change that makes Raman's so interesting. So, therefore, if there is a symmetric molecule, it will not work. That is the most important problem in Raman spectroscopy. In many cases, transitions that are allowed in Ramans are forbidden in IR. So, there are techniques, these two techniques are basically complementary to each other. So, you will see that I will show you comparable spectra from the Raman and from the IR to show you how these two techniques can be used for complementary. So, therefore, as I said, at the very basic aspect of the Raman's bands arising during measurements is the change in polarizability of the molecule. That basically sets an exclusion rule. What is the exclusion rule? It says if the molecule has a center of symmetry, then no modes is active, whether it is IR Raman. So, as you can look into this slide, it will be clear to you. So, for a molecule with a center of symmetry, as I said, no IR active transitions are Raman actives or vice versa. What is it? Let us suppose this molecule, which is COO, that is CO2, and it is Raman active but IR inactive. But on the other hand, if the molecule has change, that means if this molecule is little bit of center of symmetry change little bit this side, right side, then it becomes Raman active. On the other hand, if the molecule become fully center of symmetric, then no bands, none of these techniques can apply. As far as the history is concerned, that needs to be told, because Raman was the first Nobel laureate in science. Obviously, the first Nobel laureate from this country was for literature in 1913, but 1930 C.V. Raman got Nobel Prize in physics because of this discovery. If I want to trace back how this spectroscopic technique or the Raman effect came into picture, first thing we need to understand is the Raman is basically related to inelastic scattering. So, first time inelastic scattering, light scattering was predicted by Schmeckel in 1923, and then after 5 years, 1928, Landsberg and Mandelstam see the first unexpected frequency change in the scattering from a quartz. That is what this inelastic scattering means actually, because elastic scattering was known or even long back from Lord Rayleigh's time, but inelastic scattering was not fully understood. So, it was in early part of the last century, 20th century these things have started. In 1928, C.V. Raman and one of his students, very illustrious students, K.S. Krishnan, first time while working on different solvents saw feeble fluorescence, and it was reported. And after within 2 years, it was become so intense activity. Raman was awarded Nobel Prize. To tell you that K.S. Krishnan, this is the picture, both of them are taken from studyhelpline.net, where you can get biodata. This is Raman's picture, and this is Krishnan, just to impress you upon that in those days when India was under British rule, still there are scientists who were working on path making research, and it was only possible because of these two gentlemen who worked hard to put the things into the world's perspective as far as scientific content is concerned. So, and but Nobel Prize was given to C.V. Raman. K.S. Krishnan obviously was his PhD student who worked hard to prove that, so his contributions were nowhere less. So that is why I wanted to show you. And then 1961 laser came, and found the measure actually after the Second World War, and 1977 first time using laser surface enhanced Raman scattering was discovered. It is thanks to laser only it was possible to discover that. And 1997, that is the big change happened in the Raman spectroscopy, another big change, when single molecule shows surface enhanced Raman spectrum or scattering. So therefore, nowadays we can actually go all the way to the single molecule and get Raman scattering and then probe it using Raman spectroscopic technique. So that is how it is actually possible. As you understand, talking all this surface enhanced Raman spectroscopy and single molecule Raman surface Raman spectroscopy, enhanced Raman spectroscopy is beyond the scope of this course. So those of you who are really interested or maybe using this technique extensively, they can look at different books, which I will show you even some of the references while giving the lectures, and then understand or try to understand. But these are very advanced topics, not even part of this course. Well, to show you how the first Raman spectra looked like, this is taken from this paper which is published long back. Okay, you can see this is the spectrum, Raman's fluorescence spectrum obtained from mercury arc lamp, and this one is from benzene, okay, C6H6. So there are distinct bands you can see on the photographic plates, and these bands actually are related to inelastic scattering of molecule. Let us look into the theory in detail. That will tell you how the Raman's actually scattering happens and how it can be utilized. If I have to tell you in one sentence, Raman's effect is a 2-photon scattering process. It is no longer a single photon scattering process, and these processes are all inelastic scattering type. So first thing we need to talk about is Stokes scattering. And Stokes scattering is always inelastic scattering because energy is lost by the photon. Now if I have photon in, and obviously there is no vibration here, and therefore this photon will be absorbed by the molecule, the energy is sufficient enough for it to get excited to the excited states, and some amount of photon with a less frequency obviously will come out because some amount of has been absorbed. That is what is the nature of inelastic scattering, you should know that, and this will lead to vibrations, and these vibrations can lead to fluorescence. Anti-source scatterings, energy is gained by the photon instead of loss. So what happens, you have a photon in and there is a vibration, and then photon absorbs this molecule actually absorbs a photon. So some photon goes out, but energy is gained by the photon in this way, so there will be no vibrations. But there are two kinds of scattering, as you see, in which one is energy is lost by the photon, another energy is gained by the photon, and both are inelastic scattering type. They are called Stokes and anti-Stokes. Now there is obviously a dominant scattering process which is elastic scattering. Elastic scattering means there is no energy loss when the photon is absorbed or photon is out, and this is what is known by name of rod Rayleigh long back, and this is simple, energy absorbed, energy goes out. So, in both the cases no vibrations. So, elastic scattering cannot give this Raman scattering. If incident photon energy E and the vibration energy is V, okay, this is V. So, V, then in terms of energy we can write E minus V is a Stokes scattering, E plus V anti-Stokes scattering, and E is a Rayleigh scattering, and these two gives Raman scattering, not the last one. You should know that. These are all been taught for the different set of particles. Now to talk about more about Rayleigh scattering, this is again taken from Eugene Hecht optics book. So, if I have a molecule, you can see nucleus and the electron cloud there, and certain photon energy comes h nu, and then it get excited ground states to the higher energy state, it goes, I can see that, and then de-excitation can always happen, that means the molecule can come back to the original ground state by emission of this photon. This is fine, and this can happen in the order of 10 to the minus 8 seconds. So, therefore, elastic scattering basically lambda does not change, the wavelength of vibration does not change. It can have random directional emissions, does not lead to fluorescence, and there will be little energy loss. So, therefore, it is not, and this is what is basically the scattering energy, where these are the different parameters. The lambda is wavelength, D is the energy level, the ground state, theta is the energy at which it is scattering, the angle. Now, if I want to put the inelastic scattering into perspectives, so I can actually make a schematic diagram and show you that. So, this is what is ground state energy level E0, you can see, and then if I have some photon in the wavelength of IR radiations, the energy will be, the molecule will be excited to the higher energy level E0 plus h nu, and when it comes well, this can be also explained using the photon scattering in a energy landscape. So, as we see, I have seen that there are two kinds of scattering, one is elastic, other one is Stokes, anti-Stokes, which are basically known as elastic scattering, and they are related to Raman. So, if I consider E0 as my ground state for the molecule, and this is the vertical axis, the energy. So, whenever certain infrared radiation is imposed on this molecule, it will absorb and go to the high energy band, that is suppose the excited states, and when it comes back it emits a radiation, and that can be detected, and that is what is the principle of IR spectroscopy. Now, one can always think the Rayleigh scattering or elastic scattering in this way. We have a high energy h nu 0, by which the molecule goes to the virtual excited states, not the nearest excited state, and when similar amount of energy is released by the molecule, it comes back to the ground states. That is what I have shown you in the last slide here, exactly the same thing. Now, in case of Stokes, suppose molecule is excited to the higher energy state or virtual state by h nu 0 energy level, and there is some elastic scattering happens, some energy get lost, so that it does not come back to the ground state at all. That means it lost energy, but the molecules can come back by losing this energy h nu 0 minus h nu 1 to the excited states, the vibration states the above the ground state, that is what is this one. So, obviously you can see it can flows easily when it comes back to the ground state. Another situation can happen in anti-stoke scattering is that molecule can get excited to the higher energy states than these previously virtual states, okay, and when it goes there, it gets to these virtual states, it gathers more energy, maybe it can have h nu 1 extra energy, okay. So, that total energy of the molecule increased because it absorbed another photon other than h nu 0, and when it comes back to the ground states, it just have extra energy which is also coming out, h nu plus h nu 0. This can also lead to fluorescence. So, therefore, both Stokes scattering and anti-scattering can lead to Raman, that is what I am saying, but the catch is this, the Raman's effect comprises a very small fraction, about 1 in 10 to the 7 of the incident photons. So, that means we need to have a very good probe to detect the small number of photons which are actually undergoing this, because most of these events will be happening in the Rayleigh scattering things. Now, if I want to put it in perspectives in front of you, if I have molecule, energy goes out and energy comes goes in, energy comes out. So, that means it gets excited and it gets scattered. So, only you can see that Raman count is only 1, when that actually the laser actually which is used for the scattering is very high, 10 to the power 7 counts. So, that means 1 in 10 to the power 7 photons is scattered inelastically. So, almost bulk of the photons get scattered by elastics, and they can have, you can have different kinds of Raman spectroscopy depending on what kind of scattering is, what kind of things are happening, like rotational states or vibrational states or electronic states in the energy level. To put it in terms of IR and the Raman spectroscopy, in IR we have a laser beam, certain intensity of the energy of the given frequency is put on the sample, this one, it absorbs and then comes back to ground state, releases the energy of different intensity and detected by detector, and we get the IR spectra. In Raman, it is basically not the transmission or absorption, it is the scattering. So, laser falls on energy falls on a sample, it gets scattered because of this Raman scattering and Rayleigh scattering. This is Raman which is has changed because of the extra energy or loss of energy, and then that is what is detected. So, you have, this is the major difference between these two techniques. If I want to put it even much better way, Raman scattering sample preparation is usually simpler, liquid solid sample must be free of dust, IR you cannot do that. Biological material which usually flows, masking scattering is also possible, so which are not possible in case IR. Spectral measurements on vibration modes in visible regions, glass cells can be used, and depolarization studies are easily made. The laser radiation is almost totally linearly polarized, but in case of IR, halide optics must be used, as you have seen they are very expensive, can be broken, it can be water absorb also, because they do not absorb basically other than halides, most of the material absorb the IR radiation, and it is not possible to get a good data. IR spectrometers are not usually equipped with polarizers. On the other hand, Raman spectrometers are usually equipped with polarizers. How does the Raman spectrum look like? Well, this is what is shown you in terms in the picture. This is the intensity, this is the wave number, again centimeter to the power inverse, and spectrum is nothing but a plot of intensity of the Raman scattered radiation as a function of wave number, a frequency difference from the incident radiations usually in units of wave numbers. So, this difference is called Raman shift, incident and the scatter radiation difference, and this is for the carbon tetrachloride. So, you can see these are the frequency differences minus, and these are the frequency differences plus for the anti-Stokes, and this is the Rayleigh. So, Rayleigh will be the highest peak because this is the elastic scattering. On the left of the Rayleigh, but less wave numbers will be the Stokes, on the right side will be anti-Stokes. the elastic scatterings, inertial scatterings where energy is lost, energy is gained. So, let us look into the detailed theory of atomic vibration and Raman scattering, which can be just helpful for us to understand the simple formalisms. Well, as you know, we can always consider diatomic molecule, and with a spring attached to it, bond can be considered to a spring, and they are all getting stretched. The spring is getting stretched by mass m1 and m2, spring constant is k. So, if I stretch this molecule, that is what is excitation basically, by x1 amount this side, x2 amount is on the right side of myself. So, I can always write down, this is the Hooke's law, force law basically, m1 m2 divided by m1 plus m2, double derivative of space or the extension with respect to the time is nothing but is nothing but acceleration or decelerations. This is the mass, this is basically reduced mass you can say, and that will be related to the constant k is a capital and x1 plus x2. So, therefore, I can write down this in terms of mu dq by dt square q by dt square equal to k into q minus, this is q is the total displacement, and this can be solved with this where Vm nu m basically is equal to 1 by pi root k by nu. This is nothing but the frequency of vibrations. So, that is what is the, whenever a molecule is stretched or excited, this is what will happen, it will vibrate with this, and this will be the basically displacement can be related to the vibration this way, q equal to q0 cos of twice pi rho mu m into t. Now, if once you look at it in different perspectives, suppose this is the molecule which is vibrating as you see last time, and this is the change of the distance vibration q, and we are putting in certain radiations which is given by this E equal to E0 cos of 2 pi nu 0 t. So, therefore, this will lead to an dipole moment, induced dipole moment, that can be related to alpha into E, alpha is the polarizability and E is this E0 cos of this. So, for small amplitude of vibration, the polarizability alpha is linear function of q as you can see. So, therefore, we can write down alpha is equal to alpha 0 d alpha by dq into q and ignoring the higher order terms. So, P can be related to this way, alpha 0 A0, you can see, you can plug in this one and a big equation, and then finally after solving all these equations which I have done here in the slide, you can get elastic scattering given by this and inelastic scattering is given by this. In the elastic scattering plot, you can always get mu 0 minus mu m or mu 1, mu 0 plus mu m. So, this is basically Stokes, this is anti-Stokes. These two are the factors which are responsible for the Raman scattering. So, by just putting a simple molecular structure and then one radiations, we can always calculate the polarization or induced dipole moment, and we can see dipole moment can calculation can lead to us this kind of mathematical theory. So, therefore, if I want to give you some example, like suppose for carbon dioxide here, you have CO molecule Q plus Q0 Q, okay. So, you can see that this is what is this, there is no displacement here, there is a positive displacement, there is a negative displacement here Q, you remember. So, if I write mu 1 versus Q space, that is what will give. So, this is the polarizability, so there is a polarizability change, this is be Raman active, but on the other hand, if there is no polarizability change, this is the band in which it happens, that this will be IR active, which will not be Raman active. If the molecule is stretched or change this configuration this way, this will also be IR active, this can also show you the change in the frequency as function of Q. So, finally, again I have put down these equations where the Rayleigh, the elastic scattering and inelastic scattering events are both are given. One can do it for other molecules like water. You can see all the modes are in water actually, nu 1, nu 2, nu 3 are active in Raman and this, because this leads to change in polarizability and change in the polarizations both. If you take CH2Cl2, there are stretching and bending both possible here. So if I consider Vs, this is the stretching bands for this, or Va, P or Bs here, actually there are 3 A1, B1, A1. So that change in the stretching can lead to scattering, or you can have a bending actually. You can see this is scissoring, you can have scissoring. These are all we discussed in the IR spectroscopy, or you can have a rocking or wagging or twisting. These vibrations can lead to Raman active spectrum. So to give you little more aspects of the polarizability, if you have not understood much, so that you can go back and look at the slides. Polarizability of molecule is to the mobility of the electrons when you apply field. Basically you apply field, how the electrons move. They move symmetrically, then there is no change of polarizability. If they move and distortion happens in the field, direction of the field, okay, and then it is anisotropic. But if suppose distortion is same, this is isotropic. So more molecules, for many molecules polarizability depends on the direction of the applied fields. So direction of the applied fields, like HH easier to distort along the bonds than perpendicular to the bond, so polarizability is anisotropic. Variation of the alpha with direction is described by polarizability tensor. A tensor is another vector which can be used to detect to basically show the variation of alpha with the direction. Now vibration is active, it is if it has a change in polarizability. Any vibrations in the molecule, if you put an energy, will be active, Raman active, if there is a change in the polarizability alpha. So basically I can tell this way, polarizability is the ease of distortion of the bond. So therefore for Raman active vibrations, incident radiation does not cause a change in the dipole moment of the molecule, but it changes the polarizability of the molecule. That means it changes the electronic distortion of the molecule. It does not really change the basically dipole moment. The molecule, the dipoles are not going apart, the strengths are not changing, but their polarizability means strength of this electronic, the mobility of the electrons are getting distorted or changed. So the starting vibration going, the electric field of the radiation at time t is induces separation of charges. As you at the beginning you put electric field, it induces separation of charges, and then this is called basically dipole moment, which can be related to this P into alpha into E. Remember alpha is basically the polarizability. So we are talking about this change of alpha, not change of P, which is required for Raman. Change of P is required for the IR. Please do not get confused with the molecule's dipole moment or the change in dipole moment, because this is always often gets to be 0 for the molecule of these molecules. Again I come back to CH2, Cl2, okay. So sorry, I come back to, this is wrong, I come back to CO2. There are 4 modes of CO2, and only out of 4 only new one is Raman active. So new one is this one, CCO. So there is a change in, you can see dipole moment is changes there, is not 0. Mu3 and mu4, basically 2 or 4 they are IR active. So here mu is the dipole moment, nu actually alpha is polarizability, q is the vibration coordinate, r is basically, q is this basically the displacement which we have used that, and this is what we can show. This is new one, so you can see polarizability is changing like this. This is mu3, polarizability is changing very small, not active, but polarization is, dipole moment is changing extensively. Here dipole moment does not get changed. To give another example of benzene actually, benzene, as you know, this is has aromatic CH ring, and there is a stretch band at about close to 3000 actually, and then you have a ring breathing mode which is about 992, and Raman, this is the basically Raman shifts. You can see these are the Raman shifts, and this is the basically absolute CM. Raman shift is calculated by difference between the incident radiation and the vibration which is coming out, and this is what is the breathing mode, and this is what is stretching mode can be calculated. Now to show you the difference between infrared and the Raman, I take this complex molecule with NH2 groups. So you can see that Raman shift gives you very nice spectra as compared to the IR, and Raman shifts comes at a higher delta mu than mu actually. This is Raman shift actually, change in frequency, change in wave number, this is mu, and this is continuous here, this is the basically fingerprint regions here in IR, but the most important things comes in this higher change in the wave number regions. So this is again shown here, this is the 50 here, this is IR Raman. I can see that CO is same, but CC, this one is highly increased for Raman, and we can get other peaks also, which is very similar in this case of molecule. This again obtained from McCree's book. To give you a list of the Raman and the IR frequency for different functional groups, alkanes, this is very strong in IR, Raman is also very strong. CC stage obviously Raman is strong, but IR is not at all available. And then there are others, C triple bonds, CN, you can see strong and very strong Raman scattering. Then you have very strong IR scattering for primary these bonds, but weak Raman scattering, and very strong Raman scattering also come for CS stress, because there are a lot of change of polarizability of the molecule. This is all obtained from McCree's book. Well, there is another thing which we should also know for Raman scattering is the radiation power or radiant power. As you see, the radiant power phi r is proportional to sigma Vx, Vx to the power nu x, sorry, sigma nu x to the power 4 E0 Ni e to the power minus Ei by kT, where sigma nu x is basically Raman scattering cross section, which is in terms of centimeter square, and nu x is the excitation frequency by which you are putting the energy, laser beam energy. E0 is the incident beam in radiance, Ni is the number of density states in any state I, and Ei is the energy of that states, and this is basically exponential term comes because of Boltzmann's. So this sigma term is target area presented by a molecule for scattering, that is what is this scattering cross section. How much is that area, target area by molecule for scattering event to occur. So that can be also put it in this way. So as you see, sigma is basically this sigma, capital sigma by this is the scattering cost integration of the whole scattering for the molecule, and d sigma by sigma, this sigma means this is small sigma, this is capital sigma, is nothing but scatter flux by unit solid angle divided by incident flux, this is C, incident flux by unit solid angle. So scattering by incident, and then you multiply the whole solid angle which is coming out, and you get that. So if I have to compare this with other techniques like UV, IR, fluorescence, Rayleigh, Raman, and other surface enhanced Raman, you can see the scattering cross section is very high. Very high means not very high, 10 to the minus 18 is pretty low, but still it is high in case of UV and IR. Rayleigh and Raman, it is pretty low, 10 to the minus 26, minus 29. That is the problem actually Raman spectroscopy, you need to have a very good detector to detect this scattering events. Again for excitations, I am giving you some values for CH3Cl. Okay, you can see that these are the wavelengths, excitation wavelengths, these are the sigma values, all in the range of 10 to the minus 28 centimeter square. These are all adopted from Akora's book of surface enhanced vibrational spectroscopy. Now lastly, which we are going to talk about is the typical Raman setup or things, how it is done in the lab scale. As you can see, this is very complex. First part of this, most important part of this monochromatometer spectrograph, and then you have a laser beam which is source, which is basically passes through dielectric mirrors, then put the sample, then its radiation is collected or the scattering events are collected. It is, you can see that it falls and then does not grow like this, but it comes back at a scattering angle, collected by collecting lens, focusing lens analyzer, then polarization scrambler, and then it goes to the slits and then monochromator things. In this part of this monochromator, you have several important aspects. One is the controller, second one is the photon counter, photon can be counted by PMT, photo multiplier tube, and then you have a controller which will plot this, display this data, and then you have a display. So that is what is the basically, I think I have already discussed with you about monochromators in case of photoluminescence spectroscopy. So the spectrograph is where the data are plotted. So scattering can be done in both ways. From the laser, light can fall and scattering can happen either 90 degree this way, or you can have 180 degree coming and scattered, and then scattering falls on a lens, and again this is focused and then they are collected. This is what is shown here. collector lens, focusing lens, analyzer, and then it enters the monochromator. You can spectrographs can be for Raman's, actually this is for this A1877 triple monochromator. The whole thing is basically monochromator. This is the specs 13103, 14034 double monochromator. Let us look at first the double monochromator. So you can clearly see that these are these beam splitters or mirrors. Actually it comes and falls on a mirror M5, sorry, it falls on M1, then goes on to G1, then again M2 gets reflected, finally it comes out through this. So entrance and this, from the entrance and the exit, there are actually M1 to M5, there are 5 mirrors, and there are these splitters G1, G2, and they are all actually, and by this way you can actually get these monochromatic radiations. And otherwise you can do, what you can do is this way, you can have entrance, then it passes through lot of bands passes, finally it goes to the subtractive dispersion and it falls on a 3 turret getting assembly and then comes out. Well, we will not discuss so much of detail, but there are 2 types of spectrographs used. One is a double monochromator type, one is triple monochromator, depending on this has a better ability to collect data than this one. Otherwise you can use photodetectors, and actually nowadays people use photodetectors because these are easy to manipulate and easy to work with. Photodetector is nothing but basically you can see here you have photocathode with and then you have a within that you have electronic intensifier which will intensify, and then these are actually cooler, cold finger which will be cooling it, and you have optical fiber coupler which will couple that, and you can always use otherwise CCD cameras or charge coupled device where you can actually have pixel types in which you can detect radiations coming on each pixel. So, and what about others? In this case water can be used as a solvent and very suitable for biological samples. We know in IR we cannot use water as a solvent, it can absorb, and then because water can be used, this is very easy, biological samples can be done. Raman spectra results from a molecular vibration of higher frequencies. Spectrums are obtained using visible lights or you can near IR radiations. Glass or quartz lenses, cells, optical fibers can be used. Standard detectors always used, but nowadays no longer. Few intense overtones and combination bands like few spectral overlaps can be done. You can totally symmetric vibrations are observable. Raman's intensities are basically proportional to concentration and the laser power. This is the proportionality constant, not alpha. Well, as you have seen that this is much more simpler and cheaper than the IR spectroscopy. It has instrumentation is much less, but the lower detector limit is the problem in case of Raman. So background fluorescence can always create problem for Raman, which you will see how to take care, and more suitable for vibration with bonds with low polarizability like chlorine carbon fluorine bonds. So how to take care of this background? So if you suppose take with water and cuvette this spectra, and then separately you can take for water and cuvette without sample, for sample here is basically sodium sulfate, and then you can basically subtract and get this background removed. That is what can be done routinely nowadays for the computers. Applications, Raman spectra can be used for many applications like molecular vibrations or quantity quality analysis also. It can be done for all kinds of elements, mid-range solids, stress measurements, high pressure and glasses also. There are large number of applications. So with this I close this chapter on Raman spectroscopy. The only thing which is left over is the STEM ILS energy loss spectroscopy, which we will discuss in next 2 classes.